Hello everyone, welcome to this webinar hosted by UReason. I'm Jules Oepmans and I'm presenting this webinar to you today. I have a background in AI that started in the 90s and I've been involved many times in the past 25 years in prognostic and predictive programs that ensure asset integrity for critical assets and critical processes. I work at UReason, a software company that provides solutions for real-time condition monitoring and predictive maintenance. And I help our customers to use our technology stack on a daily basis. At UReason, we combine our domain expertise and software knowledge with our customers and help them to analyze data, asset data, and process data, and assist them to create software solutions that provide insights into the integrity and the efficiency of assets and processes. UReason has offices in Rotterdam, which we can see here in the picture on the right top side, and in Reading in the UK. Our customers are predominantly in manufacturing and process industry, and they are located, most of them in Western Europe and the Northern Americas. So UReason is active in the field of real-time condition monitoring, predictive and prescriptive maintenance. In our field of operation, we assist asset owners, OEMs, and MROs with data-driven maintenance solutions. Our software, APM Studio, allows you to set up real-time condition monitoring and predictive maintenance applications and solutions. And APM Studio is used at different levels in the automation period. It's used embedded, for example, with OEMs, monitoring faults and risks, and you could say in isolation to the asset. And an asset can be instrumentation, an actuator, a pump, a compressor, filter, etc. And we also work at level 2 and 3, where APM is used to monitor faults in relationship to the process. When deployed at level 4, APM Studio is used for optimizing the maintenance costs and planning associated to an asset base supporting a process. The topic of today is to see how we can apply and run analytical and machine learning models on live streaming data. We will have a look at what is needed to cross the chasm between your data analysis environment, where data scientists search for insights in your data, and the production environment, where the streaming data in combination with the machine learning models can be used to prevent unwanted downtime or improve asset efficiency. The world of data scientists is where data is analyzed to gain insights and try out different analysis models and test to see if they can predict a certain failure or a certain degradation of your asset or process. Once a model has been developed that has good results, for example, an accuracy of prediction failure above 80%, you want to use that result in your live environment such that it provides the insights to production and asset management on a 24/7 basis. Let me ask you a question via the webinar software. So what you should see is you should see a question popping up in your screen, which is my question to you. Do you currently deploy machine learning models in production? So do you currently have a stream work process whereby the results of machine learning, the results of the data scientists are embedded in production and used in production? So you can answer with yes, or we're investigating this, or no. And I'll wait some time for the answers to come in. So most of you, by looking at the responses, most of you are not deploying machine learning models in production yet. So this is one of the topics of today's webinar, to look at efficient ways or efficient methods of how to deploy the results that were gathered during an analysis phase into the production environment. Thanks for your answers. Oh, I think I went. Okay, so what we use to deploy machine learning models in production environments is a standard called PMML. And PMML stands for Predictive Model Markup Language, and it's a standard that represents statistical and data mining models. And it allows you to exchange the model that you've developed in your analysis environment between different environments. So you may use an analysis environment such as KNIME, and we'll be looking at KNIME in this webinar as well. And within this environment, you may have trained and validated your models. And in this environment, you can export the results of your analysis to, for example, Python to further validate your model. And you can deploy a model once you're happy with it within APM Studio. And we will also be looking at how to deploy it within APM Studio in this webinar. But there's also other ways to deploy. So some of you have actually answered the question with deploying machine learning models as well. So let me ask you another questions. What methods you use for machine learning model deployment? So there are a number of methods. One of them is called Pickles, which is a serialized form of Python. There's Onyx for deep learning artificial neural networks. There's PMML, which we're going to cover in today's webinars. And then there's plain old Java objects and model-oriented Java objects, which you can also use to deploy, but that requires a lot more programming experience. So let me know how you currently deploy your machine learning models. So there was a few of you that are deploying machine learning models. So just interested to see what methods are being used. So the answers are coming in. Most of you don't deploy machine learning models yet. Some of you use other methods. We'll come back to that at the end of the webinar, asking you what methods you currently apply. And none of you are using Pickles or Onyx or PMML at the moment. So this is actually interesting because we'll look at PMML, Predictive Model Markup Language, and explain how you can use that to deploy your models. It's quite easy and quite straightforward. Thanks again for your answers. So PMML, Predictive Model Markup Language, is not new. This has been around for many years, since the late 90s. And the standard is supported by many companies such as IBM, SAP, and Microsoft. And it's also supported in many analytical tools such as SPSS, SAS, and KNIME, but also in Weka, for example. All these tools are analysis tools, analysis workbenches that allow you to analyze your data, transform your data, and construct descriptive and predictive models on the basis of your insights, on the basis of your knowledge. So taking a closer look at PMML, and a closer look at PMML files, which we see here on the right-hand side, you can see that PMML supports various elements that you also have in your analysis workflow. They provide the translation of the functions that you have applied on your data prior to training a model. But they also provide a wide set of different predictive models, such as neural networks, support vector machines, regression models, etc. And they provide you with support to deal with the outputs, the post-processing of your model output. So it's quite a complete language that allows you to go from the inputs, the processing, predictive models, through to the outputs. And when you've trained a model and you've validated a model, you can export it as a PMML file, which we see here on the right-hand side. And these you can import into various execution environments that support PMML, and APM Studio is one of them. So let's have a look at an example. So I have data which presents functional degradations for various process equipments in my plant. And this functional degradation data is based on data which was collected from process historians and maintenance management systems. Looking at the data, so looking at the graph on the left-hand side, we do not see a clear relationship between the various pressures, temperatures, and flows that are being measured. However, if we start analyzing the data and look for the relationships, the interrelationships that exist in the data, we do see some interesting results. So let me switch now to an analysis environment. and provide you with a small demonstration. So in here I have loaded, and I have done a few transforms on my data. So I have pressure data, temperature data, flow data, data from vibration sensors, data from my coolers. And I have various labels that I've collected from a process historians and my maintenance management systems. On this data, I provide a number of transformations to combine and pivot the data that was actually collected by the process historians. And this I basically do to get all the frequencies, the time frequencies of my data into the same order. So here on the left-hand side, we see a number of steps, a number of data pre-processing steps that I've taken in order to generate a file with which we can train a model or see if we can train a model with it. So my total data set is about 13 million rows, and I have various pressures, temperatures that are measured, vibrations, flow, and cooler conditions, but I also have different labels that represent the degradation of my various process equipment, of my pumps, my valves, my coolers, etc. So if we have a first look at the data, let me zoom in a little bit for you. Let's make this a little bit bigger. If we zoom in on the data, we see the different process variables, the pressures, the flows, the temperatures, the vibration center, and the calculated cooler efficiency and some other values. But we also see different values for the cooler condition, the valve condition, a flag that indicates if I have internal leakage in the pump, and a flag that indicates if I have an issue with my hydraulic accumulator. And in this data set, we can see, for example, for the cooler condition, there is a very strong relationship, positive and a negative correlation with different process variables in my data set. I can also see at first sight, at first glimpse, that the other conditions, valve condition, internal pump leakage, etc., have not so many close relationships to my other process variables. So the color here of these cells is quite dimmed. It's not dark red or dark blue. And that indicates that there is few or little correlations in the data. So I actually need to take some additional steps to find additional correlations in that data. In here, in this environment, this is 9, by the way. I have a number of tools to train models, neural network models, support vector machines, etc. And in here, I've trained a model for detecting and classifying the valve conditions, the bad valve conditions in my data, and the cooler conditions. So in here, I'm filtering a number of columns. I don't need all the columns from the data set, but only those that are leading the features. And I'm partitioning, I'm taking part of the data, training a model with that, and taking the remainder of the data and then validating the model with this to come to an overall indication of the precision of this trained model. So what I just did is I launched a viewing component. This takes some time because there's 13 million rows involved. And it processes, it generates a view, which is going to give me insights into how precise, how good, how bad the model has actually worked on the data that I provided to it. So in here, let me try to squeeze this onto one view here. In here, I've trained a model with 70% of the data. And now I've validated the model with the remainder, the 30% of the data, where I've taken an equal distribution of the different issues that exist in the cooler. The cooler issues are represented by numeric values, 100, 20, and 3. 3 means that the cooler is going towards a failure mode. 20 means that I have a reduced efficiency, and 100 means that I have normal or full efficiency. And in this confusion matrix, we see how precise the algorithm has actually predicted the condition of the cooler based on the data that it is not seen yet. So we see that we get quite a high prediction level, above 95%. on recognizing the cooler. Sometimes the cooler condition has a false positive. It predicts that it has reduced efficiency in some of the cases. And here we see that sometimes when the status should actually be near failure, it reports that I have reduced efficiency. But overall accuracy of this exercise training, this model is pretty high. So what I would like to do is take this model and use it in a production environment such that it looks 24/7 at the condition of my cooler based on the data that is provided to it. So what I've done here, I've taken the trained model and I'm writing the trained model to a PMML writer block. And this PMML writer block allows you to export the content of the model, the configurations of the model, such that you can execute it in other runtime environments within APM Studio or within Microsoft. They have different environments in which you can run PMMLs, or within SAP, but they also have different environments to run PMMLs. Okay, I forgot to skip to this slide. So the demo I just showed you, a part of the analysis train of analyzing this data, having a closer look at, what value actually lies inside the data. And we found that the cooler condition could be predicted on the basis of a model that provided quite a high accuracy, quite a good accuracy on the classification of the cooler issues. So let me ask you two other questions. So the first one, we just had a look at some advanced data analysis tools. I'm using KNIME, which is an open source environment. But are you currently using different advanced data analysis tools? It could be MATLAB, Modelica, SPSS, SES, Orange, Python, R. I mean, there is a number of different tools and analysis suites out there. So there's programming languages, script languages such as R and Python. And then there's higher level tools such as Orange, KNIME, SPSS, SAS, Weka, and a few others. So most of you, there's already quite some answers that have come in. Most of you are using advanced analysis tools. And some of you are not using tools at the moment, and some of you are investigating tools at the moment. So let me ask you another question. And this is a multiple choice one. What tools are you currently using? So I mentioned a few, but yeah, there's many. There's MATLAB, Python, R, Orange, KNIME. Can you indicate what tools you're currently using to analyze your data and build models, validate models? So Python comes up quite a few times. SAS, yeah. For me, those are the usual suspects. R is being suggested a couple of times. And then others. I would say it's a tie break between Python and SES at the moment, which provides SES is a data lake provider. So they provide a number of analysis tools, but also PMML capable. So whatever you do in SES, you can export as PMML and then, for example, run within APM, which is quite nice. Thanks again for your answers on these two questions. So I exported a PMML model and I connected it to my live streaming. The next step that I would like to take is to connect it to my live streaming data such that I can inform users about upcoming conditions in my cooler, for example, because we exported a PMML file for the cooler, and yeah, inform the users about what is happening. So let's have a look. Let's have a look at how we do that inside APM. So this is the APM environment that we're currently seeing. This is the UI, web-based UI. And we're currently looking at a dataset that was also used to train my model on, which has different I/O points for pressures, cooler efficiency, temperatures, and these are actually the different values on which the model has been trained, and these are mapped to different objects. So, for example, the pressure is mapped to a pressure transmitter, its property, the pressure, the temperatures are mapped to a temperature transmitter, etc. So the data is actually mapped onto classes. In here, I have different classes set up. Classes are like blueprints, templates, and these can be used to capture I/O or the results of calculations. So, for example, we saw that there was pressure and temperature transmitters, but also flow sensors. And these are instruments, and we have process equipment such as pumps and coolers in my example, which yeah, in the case of a pump, for example, provide much more properties, much more capabilities, you could say. In the case of the cooler, I have an efficiency, a power, and a string, the condition to which we're going to write the condition of the cooler based on the output of the PMML model. So we have data, we have classes, a model has been created, so we have different objects. We have PS4, which is this pressure transmitter. We have PS5, PS6, and values are I/O points are mapped to it. So if and when values are updating, we will see them here. And we have a flow sensor that provides us with a volume flow as well. There's also a number of alarms defined. So there's a number of alarms defined for the cooler condition, but also for a pump. There's also a pump running in this example. And the data in this example can quite easily be visualized in different dashboards. So APM provides an environment to create dashboards so that you can zoom in or home in on, for example, the performance curve of the pump, where we see the current operating point, the previous operating points, and the area in the performance curve where you should not be, which is this purple area. And we see some historical data that represents the efficiency of the pump, the total dynamic head, which is calculated, the net positive suction head, which is calculated as well, plus the area in which you should be, the green area in which you should be. Now let's have a look at our PMML model. And what we see here is a processing rule. A processing rule is an element that allows you to do calculations inside APM. And these processing rules, let me give you an example of what you can do in processing rules, allow you to, via drag and drop, create like a workflow that is based on the object that flows into it, or which is based on a certain condition that is met. So if you if your object is in a certain state and you've detected a certain alarm, then you can do different types of operations to process the data or to, for example, do calculations. And inside this data flow task within APM, we have the possibility to create a PMML model, but also a fuzzy model and other models. And these PMML models have a configuration where you can link them to a model that you can load as a resource. We saw earlier on in the presentation that a PMML model is a XML file that describes the type of algorithm that is being used, its configurations, and yeah, we trained a neural network, so the weights of the different nodes and the number of layers in that neural network. So the PMML provides you with a descriptive language of how a model should be executed, what the configurations of that model should be. And the block inside APM allows you to connect different inputs and different outputs to a PMML model that you would like to make live. So let's have a look at our example. So we trained inside KNIME, we trained a PMML model. Here I have a processing rule that collects the cooler, and then the cooler is run into this block, data processing block, which continuously, this is a timer function, which continuously in a loop is running the PMML model based on different inputs. So based on pressures, temperatures flowing in, it's executing this PMML model, which was the result of KNIME. So that was the result of this block here. This block wrote out a PMML file. And as and when the inputs are provided to this block, it will calculate a number of outputs that are representative of my cooler condition. And this cooler condition is then is exported to um, a field on the cooler. And on the basis of that field, alarms may be generated, alarms may be shown for the cooler condition. So if we have a look here, we see that currently the cooler is in a state, and I'm running at an increased speed the data set through it with different statuses, different situations where it will have reduced efficiency, it will be okay, or there will be a failure. And as and when failure is detected, so as and when the PMML model executes and determines that it's 90% or above likely that there is a failure, it will generate one of these alarms, and these alarms can then be transmitted to the maintenance management system, or they can be sent to a message in Teams, or they can be shared in various other ways, or you can represent them, of course, on a dashboard. So I have a small dashboard here as well, which is just the condition of the cooler, the various alarms that are currently active. And yeah, these dashboards, like anything inside APM, is drag and drop, so you can quite quickly generate a dashboard and link this actually to different data sets. So let's quickly create a dashboard here for our cooler. And let's say that we would like to see the power of the cooler and the efficiency of the cooler. And well, let's keep it at this. Drag and drop, and different dialogues allow you to quickly create charts, asset tiles, pie charts, gauges, etc., which is all web-based. All web-based in the sense that this screen that we're currently seeing is running inside a web browser, but it could also run on a tablet, of course, or on a mobile phone, anywhere. And it scales quite nicely according to the device that you're looking on for that specific piece of equipment. Okay. So that was a very quick, I don't know, I don't think I went too fast, but if I went too fast, you can always reach out to me and get a more detailed demo or more explanation on the usage of PMML. With the demo ending, we've come to the end of this webinar. I have 2 minutes left. The webinar about how to apply machine learning models on streaming data. And as we saw, PMML is quite beneficial. It's a mature standard that allows you to productize your analysis results. And it's quite powerful, and it's proven itself very well. Let me ask you, and maybe you can answer that in chat, what you think on our view on how to deploy and integrate machine learning models and deploy these on streaming data. So maybe you thought this was insightful, or maybe you learned new things, or maybe you would like to learn more. You can reach out to us, of course. Or of course, you could also maybe say that it had little value. I mean, up to you. And you can use the chat for that, the public chat. Okay. So we've come to the part of questions or possible questions. So let me ask Arthur and Simas, who are the moderators in the webinar, if there's any questions. There are a number of questions that have been put in private chat. Let's see so one of the questions here is what is the typical learning curve of analytical tools you showed during the webinar? Okay, so this isn't, it's not a straightforward answer. So there are multiple analytical tools. You have the script-based ones like R and Python, and they require that you have some programming background, that you understand constructs in programming and arrays and lists and all those kind of things. And they will, because of the variability in the number of libraries that you have, they require some, bit of a learning curve, a few months, I would say, before you know all the ins and outs, specifically to machine learning and specific to some machine learning models. There are higher level tools like NIME, which I showed, and Orange and Weka and SAS and SPSS that have a drag and drop type interface, and you can quite quickly master and learn those tools. Typically, a few weeks, 2 or 3 weeks. Within the day you can train a model, but if to know all the ins and outs, 2 weeks I would say is required to learn those tools. Okay, I have another question. Is high frequency data needed to train machine learning models? Not really. It depends on the type of failure that you would like to predict. So if you're looking at shaft alignment, for example, so wear and tear of bearings, in those types of cases, we need high frequency data to train models and access also if you want to put those online to the streaming data source for those. So either via OpenC or via another method, have access to the vibration data. But typically for training machine learning models, you need the data in a frequency that still allows you to predict the different classes of failures with a high accuracy. Let's see. I have a question here from Jürgen. How are the alarms coupled to failure modes? Yeah, so if you think of an asset, if you take a cooler or a pump, you have an FMEA or an FMECA. And in the FMECA, you have failure modes, causes and consequences. And then if it's an FMECA, you have an RPN, a risk priority number that provides you an indication of how likely it is that a certain failure will occur. And the linkage of an alarm to a failure mode is or can be done on the basis of the failure modes that you've identified in an FMEA. So one of the ways, let me quickly show you, one of the ways that we provide is we provide capability of bowtie rules, and bowtie rules allow you to translate an FMEA, FMECA, the failure modes, the causes and the consequences to a causal model that runs on your streaming data, and it detects the different causes of failures we see here on the left-hand side. And in these blocks, underneath these blocks, there are different processing rules that are determining if there's a high discharge pressure, if there's a low suction pressure, etc. And then it can conclude if there's a clogged filter, a static head to low, or a bearing failure. Once this main event triggers and becomes active, then the right-hand side of the bow tie also becomes active. And in the right-hand side, we have barriers, and these barriers are looking, for example, here in the case of pump cavitation, if there is a prolonged excessive vibration, because that will then actually lead to imminent pump failure. So looking at the trend of prolonged vibrations on that pump. Or if there is a continuous low flow from the pump, then you're actually, one of the consequences is that you lose efficiency. So this is one of the ways that we can link the alarms that could be generated by an ML, machine learning model, to different causes that are contributed to a certain unwanted event. And let me just, there's another question here. There's a question here about what the detailed steps are to go from data analysis to modeling. So what we typically do is if we receive data, or if we work together with a customer and we receive data, we apply a method which is called CRISP-DM, which is a method that has been around for years, that structures the way in which you do data mining projects. And the CRISP-DM method was actually on one of the first slides. Let me scroll back to that slide. Let's give me a second. There you are. Um, you need to understand part of the business. Then there's typically an iterative process between the people that are analyzing the data. If they don't have business understanding, to better understand the business, what does the value represent? How does it relate to the process? How does it relate to the asset? Then there is a part of data preparation, and data preparation goes hand in hand a little bit with modeling, because on the basis of the outputs of your model. So, for example, the case I described was the cooler condition, but we can also detect, for example, faulty valves and leakage internally to the pump. In this data set, we need some additional data preparation steps on the data in order to do the modeling correctly. Now, the evaluation in the tooling that I was using is done completely automatically, and you have different ways like confusion matrices that I was showing to analyze the results. Now, based on the evaluation of the results, you may go back to the business understanding if you have a too low quality of prediction, too many false positives. If it's proper, then you can go to this deployment step. Let's see, there's another question from Petra. What are the costs of the model compared to the benefits? Well, before you do any data analysis and training of a machine learning model, there's a step before the business understanding to set up the business case. So typically our customers, and if we are involved as well, we focus on critical assets that have a business case, a positive business case to do continuous monitoring on, so real-time condition monitoring or predictive maintenance. And based on the business case, we determine what the added value, the added benefits would be of knowing when an asset is degrading or when an asset is failing. And we also determine if they're, from an organizational point of view, you can actually take action to react to the prediction of the model. So the cost benefit, so the cost of the model compared to the benefits, really depends on the business case. So we've had business cases with an ROI of a few weeks. We also had business cases with an ROI of 6 months, 6-7 months. But not always is it possible to express the business case in a value. It's not also always needed either. There are also cases where the business case is actually risk reduction or an improvement of the asset integrity. So not all our customers are focusing on the, let's say, the financial benefits, but some of them are also focusing on benefits that are related to risk and asset integrity, because they have a certain supply of product or a certain risk containment that they need to strive for. One of the questions here is Michael. Did I understand it correctly that the machine learning models can run on a local PC, no cloud infrastructure is needed? Yes. So everything, that's a good question. I maybe went a little bit too quickly. So everything we just saw, including APM, is actually running on my local machine. And let me just show you this slide again. So APM can run at different levels. At level 0, embedded, where if there's sufficient compute power on an asset, instrumentation, actuator, pump, filter, etc., then we can run embedded, because typically on an asset, the amount of I/O that you have available is a lot lower. The frequency, of course, is a lot higher of the data there. But we can run machine learning models embedded with APM in Linux environments, in contained Dockers, and very different other deployment methods. This is typically done by the OEMs, and it's an asset in isolation as such. But as you can see here, typically up to level 3, we run on-premise, and that can be on edge computers, or it can be on local on-premise compute, PC or servers. The size, so the size of your application, the amount of I/O, the update frequency, the number of models that you would like to run are determining how big or small the compute should be. So how big or small the PC or server should be, or the edge computer on which you're running. But yeah, we typically run on-premise, and we can run in cloud as well, of course. So another question here: how do you manage a deployed machine learning application? That's a good question. If you, I mean, the data scientists are working in environments where they may have, more than enough compute resources, more than enough memory, more than enough CPU, etc. But in a production environment, you may not have sufficient resources, and you need to keep an eye on the execution of the models. On the production side, what we typically do is that many of the models provide you with an accuracy of the prediction. And based on training data and validation data, we determine what the bounds, the boundaries are of the prediction level. And we keep a close eye. So each time that a PMML model is executed, we keep a close eye on the accuracy of prediction. And if that accuracy of prediction is varying too much, or when it goes below the low boundaries, for example, 80% or 85%, then we signal the maintainers of the application to evaluate if a model update should take place. So in the production environment, you may have fouling or influences that are caused by seasonal influences. So, for example, in a refinery, you may have summer grade and a winter grade of diesel that you're producing that provides you with a different set of data inputs, different variation in the data inputs, and you need to take care of that. You need to take that into account. So you need to monitor the accuracy of your ML model, the output accuracy of the ML model, and take appropriate actions when it's not not within the boundaries anymore that you can set yourself. So another question here: who owns the models and algorithms that I've generated in APM Studio? You do. We provide the tooling, so we provide you with the capability to set up bow ties. We also provide you with templates and blueprints for typical equipment such as compressors, turbines, pumps, filters, valves, control valves, and some other typicals as well. But the actual application, so the actual deployed application and all the IP is your ownership within APM. It's not our goal to own your IP. It's your IP. And we want you to reason. So that's also the background a little bit behind the name. We would like to enable you to reason on your real-time data and events. Okay, is there any other questions? I'm looking at Arthur or Simas, who are moderating. You don't see that, but they're moderating for me in the background. No, I think those are all the questions. Okay, I would like to thank you all for attending the webinar. And I would like to wish all of you a very good summer. And we will continue doing webinars on in-depth and on vertical topics. So keep an eye out for the next invitations, and looking forward to see you online again. Thank you very much.